Okay, so 12.3, we actually give a formal definition of the regression line. And it really is just a linear equation where we've got a is the y-intercept, b is the slope, x is the independent variable, y is the dependent variable. And we have calculations based on sample values of x and y for the slope, b, and for a, the y-intercept. Now we're not going to actually be using these formulas to calculate those values. I've put together a spreadsheet that we'll use not for this part of the chapter, but for the next part that we start on Monday. So I used that tool to come up with A and B for our basketball example, and it gives us A equal to 1.4, B is equal to 2.6. All right, so given those values for A and B, we can write down the regression equation. So all that's asking for is what is y equals A plus bx. Now, the textbooks and actually a lot of places will, when we are doing the summary, we will do a y hat when we're doing this the equation based on the statistics, the descriptive statistics A and B that are based on the sample. All right, so we're just going to rewrite that y equals a plus bx, replacing the a with the 1.4, which again, I used my spreadsheet tool to calculate that, so that's not something that you would have had needed to calculate. Okay, so that is the regression equation for the basketball example, right, where we have x is equal to the number of hours practiced, and then y is equal to the points scored in the game. All right, so just a refresher of what these things mean. When practice, right, which is x, equals 0, that means that it is the y-intercept 1.4 is the mean points scored when the practice is 0. And then to interpret the slope, 2.6 is the amount y, or points scored, changes for a 1 hour change in practice. Okay, so the practice hours is x, the point scored is y. So we're just relating this particular y-intercept and slope to this particular application. Okay, so we have a couple other statistics that go along with doing linear regression. The coefficient of correlation and the coefficient of determination. And these two statistics that we calculate, they're going to be values. They describe the adequacy of a linear equation to represent or model the relationship between this bivariate data, x and y, that we have. So first one is the correlation of coefficient. We use an r, lowercase r, to stand for it, and it measures the strength of the linear relationship between the two variables. So I want to emphasize linear because R only measures linear relationship. It doesn't have any ability to measure any other kind of relationship between x and y. So I have the formula there, but again, we're going to use the spreadsheet tool to calculate R. And again, we're not going to use that this time around, but next time I'll introduce that. So the correlation coefficient takes on values in between -1 and +1. And the value that it takes is going to tell us about the linear correlation. So if R is less than 0, so it's between -1 and 0, that means that x and y have negative linear correlation. Oops, sorry, let's go back. That means that x and y have positive. Positive R means a positive linear correlation. So if it has a positive linear correlation, that means the slope is also positive. All right, because that means that the line is going to increase as x values get larger, and which also means that y increases as x gets larger. Then the closer the R value is to 1, the closer it is to 1 away from 0, the stronger the correlation. So a correlation of 1 would be perfect positive correlation. Right. If R is less than 0, then x and y have negative linear correlation. The slope b is also negative, and y values are going to decrease, and the lines slant down as x increases. And the closer R is to negative 1, the stronger the correlation. All right, so negative 1 would be perfect negative linear correlation. So the closer it is to 1, the stronger that correlation is. Now, if R is equal to 0 or close to 0, that means there is no linear correlation. So 0 for R tells us that these two variables, x and y, have no correlation that can be described as linear. It means that there is no pattern in the scatter plot that looks linear, or if we can find a pattern, it is a horizontal line. And that means that there's no slope, and the slope would be equal to 0. Okay, so no slope means the slope is equal to 0. So let's look at our scatter chart, or our scatter plots again, and now relate these to what values of R they are. So this scatter plot, we obviously have y increasing as x increasing. We said we had positive linear correlation. That means that an R value for this sample of x and y values would be positive. It would be greater than 0. And then the next one, where y is decreasing as x gets larger, R would be negative. And then the next one, where we have no discernible linear correlation, and if we did, we would say it was a horizontal line. That tells it that R is equal to 0 or close to 0. And then in this last one, where there's clearly a relationship between x and y, but that relationship is not linear. Here, R does not measure the strength of that correlation because it's not linear. All right, so you would get some value for R, but it would really have no bearing. So the key thing is that to determine a linear correlation, you really need to have two things: a scatter chart or a scatter plot that looks linear, and are both determine linear correlation. So those two things are important to have. You got to have both. All right, let's look at some values of R and determine what type of linear correlation it looks like we would have. So if R is equal to 0.85, that is fairly close to 1. Okay, it's not too far off of a positive 1. So here we would have a positive, all right, because it's a positive value, linear correlation. And because it's very close to 1, you could say that it is strong linear correlation. Positive, strong linear correlation. All right, if R is equal to negative 90, because it's negative, so that means we're going to have a negative linear correlation. We're assuming we've got scatter plots that look like a linear correlation. And it's also fairly close to negative 1, so that would be negative, and it would be strong. Now look at R equals 11. It's positive, so it's indicating a positive linear correlation. But since it's closer to 0, it's not strong. The linear correlation would not be as strong as like the 0.85, so classify that one as weak. And then R equal to negative 0.02, that negative says that it's a negative linear correlation. But again, it's fairly close to 0. It's really close to 0, so that correlation is weak. Now, one thing we got to remember about correlation is that it doesn't imply causation. I'm trying to emphasize as we go along that there is a correlation or a relationship between X and Y that we're measuring with R and measuring with the scatter plot. It doesn't necessarily mean that whatever X is causing Y to happen. So that is really critical to remember. Strong correlation does not suggest that X directly causes Y or Y causes X. So a way to remember that is correlation does not imply causation. All right. All we can say is that X and Y behave in a certain way together. They kind of go together and happen in a similar pattern in relation to each other, but doesn't mean that one causes the other. Okay, so that's correlation coefficient. The other measure that we're going to look at is R squared, and that's the coefficient of determination. And it literally is just R squared. So if you're given R, to get R squared, you just square it. And what R squared measures is the variability of Y, the dependent variable that is explained by the linear relationship between X and Y. Okay, so it's going to be positive because if R is negative and we square it, we get positive, and it's going to be a percentage. So R squared is a positive percentage. Okay, so let's look at R and R squared for our basketball example. Okay, so R is something that we're going to use the spreadsheet tool to calculate. So that value is 0.96. Don't worry, that's not something that you're able to calculate at this point or have access to. And if we look at that value, we can make an assessment of the correlation between hours practiced and points scored. We know the scatter chart looked like there was a linear relationship, and this R value is pretty close to 1. So that can indicate that we have a strong positive linear correlation. Okay, now for the part 2 of this chapter, you can see that in the next section, 12.4, there's actually a hypothesis test that's based on R that actually will give us a statistical way to determine whether there is linear correlation or not. So it's not just our subjective judgment looking at the scatter plot and looking at this value of R that determines linear correlation. We're actually going to look at a statistical or a hypothesis test that will tell us. So that'll be next time. Okay, R squared, we really will just take that value of R and square it. That gives us 0.9216. So if we write that in terms of a percentage, and let's round to 2 places, we can say that 92% of the variability in points scored is explained by the relationship, the correlation between hours practice and points scored. I'm going to abbreviate a little bit there. Okay, so 92% is a pretty big percentage. If Amy was looking at this analysis, I think she's going to keep doing that practice because there's a 92% of the difference, the change in the point score that she has is explained by how many hours that she practices. So definitely worth her time. Okay, let's look at another example. Ornithologists, who are scientists who study birds, tag sparrowhawks in 13 different colonies to study their population. They gathered data for the percent of new sparrowhawks in each colony and the percent of those that have returned from migration. Okay, so I have a list of sample data for the 13 colonies, and got for each colony there's 2 variables. We have data values for each variable, the percent that are returning hawks and the percent that are new hawks. And we want to go through and identify the important pieces of information here. Okay, so what would be the independent variable and what would be the dependent variable? So this could maybe go either way, and I'm really taking my best guess based on the fact that I'm not an ornithologist, but it seems to me that the percent return would be the independent variable. Sometimes it's really obvious which one would be the independent, which one is the dependent. Sometimes not so much. So that would make the percent new be the dependent variable. All right, so let's look at this next thing. If we are given that A is equal to 84.5 and B is equal to negative 1.8, what is the regression equation? All right, so we are just going to rewrite y equals A plus B x with those values in there. So we're going to have y equal to A, which is 84.5, plus, although if we look at B, it's negative, so that's going to be a minus 1.8x. Okay, the slope is negative, and so that matches up with what we're seeing in the scatter chart, where it definitely looks like there is a negative relationship between x and y. As x gets larger, y values are getting smaller, right? And we've got that negative trend slanting down as we go from left to right. Let's look at the next question. What happens to the dependent variable as values of the independent variable increase? So what happens to the percent of new hawks as the values of a percent return variable increase? Okay, well, it is decreasing. It decreases. So the percent new, which is the dependent variable, decreases. Okay, and we know that because of the 2 things, because we have a negative slope, and we can see that from the scatter chart as well. So based on that scatter chart and R, we want to describe the linear relationship, the linear correlation, in terms of each of these things: strong or weak, negative or positive, linear or nonlinear. Okay, well, from the scatter plot, it definitely looks like it's linear. And because slope is negative, and what we see in the scatter plot, we can say that it's a negative correlation. And I got to give you R to be able to answer that question. Here we have an R value. Okay, R that I got from the spreadsheet tool, which at this point you don't have, so that'll be given to you. R is a negative 0.75. Okay, so that is still fairly close to 1, positive 1. Now it's getting into that area of like, well, how do we decide strong or weak? And again, right now we are just using our, best subjective guess. And I'm going to just circle strong there. Next time, the next part, we will actually have a hypothesis test that will make that decision for us. All right, coefficient of determination. So given R, we can calculate R squared. That's the coefficient of determination. So we take that negative 0.75, square it, which gives us 0.5625. So rounding to 2 and writing it as a percentage, we get 56%. All right, explaining what that means. So 56% of the variability in the dependent variable, so the variable that we have called y, which in this case is the percent new, percent of the new hawks in the colony, is explained by the correlation with the percent of returning sparrowhawks.